Hi, everyone. Welcome to my lecture, part of the GROWTH Astronomy School on observational techniques for transient studies. My name is Brad Senko. I'm a research astrophysicist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and also an adjunct professor of astronomy at the University of Maryland, College Park. GROWTH stands for the Global Relay of Observatories Watching Transients Happen. And we're an international team of astronomers that have joined forces to explore the dynamic universe uninterrupted by daylight. We use a network of observatories in a way similar to a relay race. The baton is passed from one observatory to the next as the Earth rotates and daylight breaks in different locations. That allows us to react fast when interesting explosions are detected and reported by wide field surveys. But being fast is just one important aspect in the discovery process. The other one is to be able to look at cosmic objects at various wavelengths, each revealing different properties in physics. And that's really what we're going to focus on in this particular lecture. The lectures and tutorials in this school will walk you through various tools and techniques that will allow you to explore transients at all wavelengths. And so here we're going to focus on X-ray astronomy data analysis. Why don't we jump in here? First, let's make sure we're all on the same page when we define what is an X-ray. How does it compare to light at other wavelengths? Traditionally, the X-ray bandpass is broken down into two different energy ranges, what are called soft or low energy X-rays. So start at somewhere around 1/10 of a keV, pushing up to somewhere on the order of 10 keV. There is no hard sort of cutoff for this, but this is typically the range that's usually defined for what we call soft X-rays. And they're called soft X-rays because they attenuate quite rapidly in water in particular. So even pushing up to energies of 10 keV, they're only able to penetrate less than 1 millimeter through water. When we think about X-rays, when we think about X-rays in the medical context, what we're usually thinking about are hard X-rays. So these are X-rays that are in the energies of 10 up to 100, maybe a few hundred keV. These are able to penetrate through significantly larger amounts of water, through skin, through various materials. And so when we think about X-rays, when we go to the dentist or we go to the doctor or when we're at airport security, these are the types of energies that we're usually thinking about here. Why do we actually care about X-rays? What can they tell us? Well, I'll just take a quote from our fearless leader. If you want to be a budding time domain astronomer, you have to be wavelength agnostic. Each wavelength tells us about very different processes that are going on in any individual object. Generally speaking, optical, ultraviolet, infrared radiation, these are probing thermal processes. This is where material is able to reach a similar temperature. At high energies, X-ray energies, in particular harder X-ray energies, gamma ray energies, there are very few systems that are able to generate thermal emission at these kinds of temperatures. And so we're really probing non-thermal emission where particles are able to be accelerated to very high velocities, where we can probe the engines, the inner regions. This is a really nice picture here of the Crab Nebula, where you can see when you're looking at optical wavelengths, when you're looking at ultraviolet wavelengths, you're seeing radiation coming from very far from the central source because it has a lot of time to thermalize, and it can also be absorbed by dust. The X-rays are actually coming from the sort of very center of this region and telling us about the compact object at its core, about how it can accelerate particles to high energies, and what's actually going on in sort of the inner regions of the densest and most energetic phenomena that we know of in the universe. A really fundamental and key important point is that X-ray astronomy is by default space astronomy. If you look at the transmission of the atmosphere, the optical bandpass, it's quite transparent to optical light. It's no surprise that some of the biggest telescopes, some of the most sensitive instruments that are observing in the optical, they're sitting on the ground because it's much easier to observe at those energies. But once you get above sort of the near ultraviolet, something like 300 nanometers light or so, the atmosphere becomes completely transparent to these energies. This is really good for us. This is quite energetic radiation. It could cause disruption in our DNA, breaking it apart, leading to mutations for a variety of biological reasons. We're very glad that X-rays can't penetrate through the atmosphere. But what that means is that if you want to observe at X-ray wavelengths, you need to be quite high up. And that means either you need to be in a balloon or you need to be in space. And this is really where NASA comes in. So NASA operates a suite of observatories that are probing the X-ray sky, different energies, different resolutions, different fields of view, but all from space, and why NASA is so keen and interested in, has a long history in this particular area. It's also quite fundamental to understand, if you want to know about the data products you're going to get from X-ray telescopes, to understand that X-ray telescopes really don't function in the same way that optical telescopes do. If you think about an optical telescope, you have a mirror that's sort of like a light bucket here. Light comes down and hits it at a normal incidence, so at 90-degree angles, and reflects back to a central collecting point. That does not work for photons that are coming in with energies that are so X-rays, with energies that are at X-ray wavelengths. They just have too much energy. Any kind of normal material, they'll penetrate more or less straight through or be absorbed. And so you have effectively two options if you want to observe the X-ray sky. The first you can see over on the left here is what we call coated masks. And so this idea is quite creative. If you think about, you have a sort of mask or imaging plane that you populate with absorptive materials, small tiles, for example, of lead. If an incoming X-ray photon hits one of these tiles, it will be absorbed. It's very dense, very thick material. But then there are also gaps in this mask. There are holes where X-ray photons can penetrate directly through and illuminate a detector. Now, if you stick these tiles in some kind of pattern, whether it's periodic or random or however you want to do it, depending on where your source is located on the sky, it will generate a very different shadow pattern on your detector down here. And so using this technique, we can actually back out by the shadow pattern that's generated on our detector where on the sky sources are located, which is very important for understanding what kind of objects we're looking at. So that's one technique, and it's very powerful. The other is what we call grazing incidence, or these are also called Walter 1 type optics. Instead of reflecting at 90 degrees, X-ray mirrors actually are reflected sort of very shallow angles. For soft X-rays in particular, these angles are of order 1, maybe in the most extreme case, up to 2 degrees. And by coming in at these very small angles, the photons are not going to be absorbed by the material. And instead, they can be reflected in the same way that optical light can be. And if you have two sets of them, in particular, this pair of shapes known as a parabolic segment and then a hyperbolic segment, you can show that an incoming plane wave here will be reflected down to a focus. And so you can actually get proper focusing imaging in the same way that you do in optical telescopes, but instead using this very different technique where we're using very shallow or grazing incidence angles. The benefits of using coated mask telescopes is that you can have an extremely large field of view for the instruments. The field of view is basically just set by how large a mask you can create on the sky. And this is on the right here, the largest one that's been built to date on the Burst Alert telescope on the Neil Gehrels Swift Observatory. The diameter of this coated mask, where you can see all the tiny little lead tiles here, is about 2 meters or so. And this allows us to have a field of view that's roughly 1/6 of the sky at any one given time. It's very easy to make coated mask telescopes that can be sensitive up to quite high energies, certainly all throughout the X-ray bandpass. You just need a mask material that is able to absorb X-rays up to those energies. You can get very large collecting areas using this technique. Effectively, the collecting area is just going to be dictated by the size of your mask on the sky. The downsides are that this leads to a very high background. You're not actually focusing the X-rays in any way. And so the field of view that you want to get, you're going to have to populate a large area with the detectors. And so you're going to have a correspondingly very large background. And that's really going to limit the sensitivity for faint sources from these kinds of instruments. Also, even though you can do localization, you can tell where on the sky sources are coming from, it's much poorer, much cruder than is possible with a focusing telescope. For example, the Burst Alert telescope, the BAT on Swift, which I believe is one of, if not the most precise localization of any coded mask instruments. It can localize sources on the sky to sizes of a few arc minutes. Whereas of course with focusing X-ray telescopes, we can do much better than that. We can get down to sizes of only a few arc seconds. So a few examples of this, I mentioned the Burst Alert telescope on Swift, the Rossi X-ray Timing Explorer, the CZTI instrument on AstroSat, which is the instrument that we'll play around some data with when we do the hands-on tutorial after this lecture. As I said before, on the other hand, grazing incidence or focusing telescopes are able to provide excellent spatial resolution because their detectors can be very physically small because of the focusing. They can have very low backgrounds and thus a much higher sensitivity. The downside is that typically their fields of view are smaller. A real challenge for space-based astronomy, they have a low ratio of effective area to mass. You can see here, in order to get this kind of focusing, you need to use a lot of material, a lot of telescope. And because it's coming in, the light's coming in at a relatively small incident angle, you only have a relatively small effective area on the sky. And for the question for space-based astronomy, it costs a lot of money to lift things up off the ground and put them in space. Anytime you add mass, that increases cost. And so that's a real challenge. The other thing, because the focal length, because the incidence angles are quite long, turns out the focal lengths can be quite long, somewhere on the order of 10 meters. So these are quite long, complex, expensive things to get up there on the sky. The sort of best known examples at the moment, the Chandra X-ray Observatory, XMM Newton, which was launched by ESA, NuSTAR, which focuses on the hard X-rays, the first focusing telescope at hard X-ray energies, and that X-ray telescope, which is another instrument on Swift. So here's just a quick exercise to get you thinking about this sort of normal incidence optical telescope versus grazing incidence X-ray telescope. The mirror assembly on Chandra remains, in my opinion at least, the most complex telescope, just telescope, not instrument observatory, but telescope ever constructed in astronomy. It's extremely large. The precision with which the mirrors needed to be coded, you can think about if you're focusing X-rays, you need your optics to be more precise than the wavelength of the light. X-rays have very small wavelengths. And so ensuring that the optics are not going to unnecessarily scatter the light implies that they need to be extremely smooth. As an exercise for you all, I suggest you look up the peak effective area of Chandra. And just do a quick Google search for this, and then convert that to what would the equivalent size of a normal incidence optical telescope be. So basically you're comparing how much effective area, which is directly related to how much sensitivity a telescope has, of the most powerful X-ray telescope costs more than $1 billion, and see how that compares to what's currently being done by optical and near-infrared because of the difference between this grazing incidence and normal incidence optics. So I'll pause for a moment there, let you take a look at that, and then come back to the lecture slides in just a moment. All right, if you need, you can pause the video if you need a little bit more time. Otherwise, maybe this is something we can talk about when we have the question and answer session. But I hope what you get out of this is that the largest effective area of an X-ray telescope for an optical telescope is actually quite small and almost something you could have in your own backyard. So we talked about telescopes. I'm going to talk very briefly about X-ray detectors. Most modern focusing X-ray telescopes employ charge-coupled devices, or CCDs. This is very similar to what we learned about when we were going through the data reduction from optical telescopes. The biggest difference, that they have a much faster readout. Rather than taking tens of seconds, in some cases minutes, to read out. Most X-ray CCDs can read out on a time scale of order a second or maybe a few seconds, some cases smaller depending on how large they are. But really the most important difference between an optical CCD and an X-ray CCD is that optical CCDs are actually able to provide energy resolution. So in addition to the location of the photons that are detected by X-ray detectors, they can also provide information about what the energy of each individual photon that hits the detector is. And that's a really powerful technique that allows us to do both imaging and spectroscopy simultaneously, something that we definitely can't do, at least with CCDs in the optical. It's worth mentioning very briefly here that future generations of X-ray instruments are going to employ microcalorimeters. The physics of these devices is very different. The bottom line from an observer's point of view is that they can provide much higher spectral resolution. Instead of spectral resolution of order of 100 or a few hundreds that you might get from an X-ray CCD, talking about X-ray spectral resolution of several thousand, maybe 10,000. Comparable to what you might see from a medium or even a high resolution optical spectrograph. And this will be really powerful, enabling really new, interesting science, X-ray wavelengths that optical astronomers have been, sort of bread and butter for an extended period of time. The data products that comes out of these devices, whether they're CCDs or kind of any other X-ray telescope, in optical astronomy, you're generally used to working with an image. Maybe you'll learn in the next lecture about radio interferometry. You see a visibility array, the product of correlations between a bunch of individual radio antenna. In X-ray astronomy, really the primary data set we usually work with is called an event list. What this is it's a table of potential photons, a four-dimensional array, where for each photon that hits the detector, you get an X and Y position on the detector, you get a time associated with when that photon hit the detector, you get an energy associated with that individual photon. Now, most pixels are empty, unlike the optical, where you have this very large background, where you have a large number of sources in any sort of given location on the sky. The X-ray sky is much quieter. The X-ray background typically is much lower. Every photon is precious. So rather than every time the detector is read out every second, giving this sort of full pixel list with a large number of completely empty pixels, what we get is an event list. Every time something hits the detector, we get X, Y, time, and energy. And so data analysis in X-ray astronomy really boils down to three things. You can slice up this event list in different ways to get different data products, all from the same data set. If you want to make an image, you just take the event list and say, okay, over some period of time, over some energy range, show me in a two-dimensional XY sort of frame where all these photons hit the sky. If you want to make a light curve, you can say, all right, I know where my source is on the sky, I know X and Y, I know the bandpass I want to look at, show me what the time evolution of this source looks like. Or if you want to make a spectrum and know something about how the energy of a source changes as a function, how the flux of a source changes as a function of wavelength, specify X and Y, specify a given time range, and say, show me how many different photons have different energies in this particular window of data space. So the data products that are generated by effectively all modern X-ray observatories are FITS files. You should be used to working with these from the optical lectures. Typically, these are multi-extension FITS files. The extensions can be images or tables. The convention in X-ray astronomy, at least, is usually that extension 0 is always an image, even if it's empty. Typically, extension 1 is our events table, again, where we have this X, Y, time, and energy. And usually after that, we have what are known as good time intervals. So what are good time intervals? Most of the most sensitive X-ray observatories, like XMM and Chandra, are in highly elliptical orbits that take them quite far away from the Earth. So when they go quite far away from the Earth, they go outside of the sort of magnetic field of the low Earth orbit, which acts to protect satellites that are relatively nearby the Earth from incident flux from the solar wind, charged particles that are flying around our solar system. And so both XMM and in particular, but Chandra also to a lesser extent, are frequently affected by soft proton flares, where you see this very high elevated rates of background counts, usually from, like I said, solar flares. So you can see a plot over here on the right where this is the background in some region of the detector from XMM. And for the bulk of time, this is of order 3 by 10 to the 4 seconds. So pretty sizable chunk of time here. This background is low and quite steady. But then for some period of time, the background just goes extremely high. These are really not possible, or somewhere between not trivial to not possible to predict in advance. So usually you just have to look at the data when it comes down, but these will be flagged by the software that processes them to tell you, okay, here's when a good time interval for these observations were. Another example of good time intervals, in addition to just background flares, if you have a satellite in low Earth orbit, if you imagine that you want to stare at a given object for longer than an orbital period, which in low Earth orbit is going to be something like 90 minutes, you can't do that continuously because eventually the Earth is going to block you from seeing the source that you want to see on the other side of the Earth every 30 minutes out of every 90-minute orbit, roughly speaking. So those can also be flagged as, good time intervals, is when the satellite you're interested in could actually see the source that you're focusing on, as opposed to when it was on the other side of the Earth. That can also be flagged in the data set as a good time interval when you want to look at the data and actually do the analysis for your source or sky area of interest. So X-ray imaging analysis. The nice thing about X-ray analysis is that it's really sort of as the basic fundamentals is if you can count and if you can take a square root, you can do X-ray data analysis. It's really as basic as that. And the reason for that is because you have very low background rates. Very rarely are sources going to be in the background dominated regime. And for that matter, almost always we have low source count rates because there aren't a lot of sources that can generate lots of X-ray on the sky. And so the emission of photons we can treat as a random process that's described by a Poisson probability distribution. So this gives a probability of n events occurring depending on the mean number expected. If we have a mean number mu expected, let's say we expect to detect one event in a given observation, then we can calculate using this simple formula, what's the likelihood of us seeing 0? Oops, it's pretty high. What's the likelihood of us seeing 1? And then it falls off quite quickly after that. There is some probability of us seeing, 4 events. If we did, 1,000 trials, maybe we would see, given this, it looks like it's about 1%. So maybe we would see 10 of them where we saw 4 events, but it's not very likely. On the other hand, if you had a mu of 4, you can see it's peaked around 4 or so, but it falls off. And then as higher and higher numbers, it gets more kind of smoothly defined and approaches what you may be more used to in this sort of Gaussian regime. So really, The Poisson equation, the Poisson formula really dictates all of the statistics that we use for X-ray astronomy. So I want to have another little exercise here just to get you sort of thinking about Poisson statistics. So imagine we're looking at a source with an X-ray telescope. We know from earlier observations that this source has an average count rate of 1.25 photons per second. You just know how bright it is. It's a steady source. It's not varying. We have the same instrument, all this information. How many photons would you expect to detect in a 10-second exposure? Why don't you think about that for a minute? Again, I'll give you just kind of 30 seconds or so to think it over a little bit. I suggest looking again at this Poisson formula that we saw on the previous slide, and then I'll walk you through it after you've had just a moment to think about it here. Okay, again, if you need to, if you're watching this at home, feel free to pause, take as much time as you need, but now I'm gonna actually try to walk through the answer to this a little bit so you get, just sort of some familiarity with working in the sort of low number statistic regime. So we said the mean count rate was 1.25 counts per second. You have a 10-second exposure. How many photons should we see? You might say, well, 12.5, you just multiply those two together, but you have to remember that CCD detectors, they only see integer numbers. So we're never gonna see 12.5 photons. So you say, okay, well, maybe we'll see 12, maybe we'll see 13, maybe your answer is 9. The honest answer, all of these is maybe. It's a probabilistic statement. So the probability of seeing exactly 12, given this, mean number of 12.5, you can calculate that using the formula here. That turns out to be about 11%. Probability of seeing 13 also turns out to be 11%. The probability of seeing 9, you might have thought, oh, there's no way you're going to see 9. That's much less than 12.5. It's actually quite high. It's almost 8%. And so if you repeated this experiment 100 times, 8 of them, you should expect to see 9 photons in it. So again, this is a probabilistic, is the way you need to think about seeing these photons, seeing these observations, and it's all guided by Poisson's equation. So that's sort of the basic counting statistics. Why did I say you need to be able to take a square root as well? So that gets into the question of uncertainties associated with each of these measurements, which of course are fundamental to any kind of scientific observation. So the mean of the Poisson distribution, as we said, is mu, which is not surprising. That tells us it's a nice statistical distribution. But the nice thing about the Poisson distribution is that the variance is also equal to mu. And so put in a different way, the standard deviation, which is what we usually work with, is just the square root of mu. So in our previous example, if we had detected 12 photons, we can easily calculate the uncertainty in that measurement and just say, take the square root of that, which is 3.5. And if you want to know what your signal to noise ratio is, it is just the number of photons you detect divided by the uncertainty in the number of photons. And so 12 photons leads you to a signal to noise ratio of about 3.4. You can see if you run through this in a couple of different examples that for brighter sources, the signal to noise ratio increases quite rapidly. So if we just increase the source count rate up to 100, the uncertainty goes down, to 10, and the signal to noise ratio goes up to 10. And so brighter sources have much higher signal to noise ratios than fainter sources. Fainter sources are very often you see low signal to noise ratio because of this Poisson sort of square root standard deviation. It's worth emphasizing here that all of this neglects background. Of course, this is assuming an idealized world in which there are no photons that are unrelated to our source in our region of interest. So let's now take a look at, an actual concrete on-sky example of how we would go about calculating this with actual data to get you a sense, and also folding in the background into that estimate. So here's what an X-ray image looks like. When we talk with our communications folks, our press people, they ask, do you have nice images? Occasionally with Chandra you will, but for most other X-ray telescopes, honestly, it looks much more like this, which for the public is perhaps not the most exciting. But for scientific, we can really learn lots of information. So I get excited about these nonetheless. So this is an observation of the transient AT 2018 COW, the famous COW, fast blue optical transient. If you have questions about that, I can answer lots of them, but this was particularly exciting source because it was X-ray bright and showed some pretty interesting X-ray variability. This is an observation taken by the X-ray telescope on board Swift. So you can see I've drawn two circles here. The inner circle, which is what we're going to call basically our source region. And typically what we'll do for each instrument, we know roughly how large a point source should be. And so we'll draw a circle that's about as large as we know the point spread function, or how large a point source will be in the instrument. We count up all the photons that are in that circle. We call this our source region. And then we take another circle that's larger than this, which we don't think there are any sources in, and we call this our background region. And we add up all the counts that are in this background region, and we divide by the number of pixels that are in this background region. And that tells us how many background counts there should be in our source region per pixel. And then we need to multiply by how many pixels there are in this source region. So for this specific example, which had an effective exposure time of about 10 kiloseconds, if we just add it up, it's hard to see here from this particular view, but if you added up all the individual source counts that were in our region of interest here, you should see 11. You could then, using the larger annulus on the sky, calculate how many you would expect to see in the background region, just due to background unresolved X-ray sources, solar flux, charged particles from the sun flying around the solar system. All these things contribute to the X-ray background. And so if you subtract those two, 11 minus 1.3, that's 9.7 source counts in our source region. You can convert that to a count rate, just dividing by the exposure time. So 9.7 divided by 10,000 gives you a count rate of 9.7 times 10 to the minus 4 counts per second. And by taking the square root on the number 11, which is the number of counts in our source region, this gives you the uncertainty in the count, in the number of counts in our source region. So in this particular observation, 9.7, or roughly 10 counts, corresponds to a signal to noise ratio of about 2.9 actually. So this is a 3 sigma measurement of the count rate, the flux from this particular source. One of the interesting things about X-ray astronomy, however, is that even though the signal to noise ratio of this observation is only 3, the significance is extremely high. We can say that there is a source there with a very high degree of confidence, greater than 5 sigma, higher than 99.99%. And that's just effectively the ratio between the expected number of counts, 9.7, and the counts in the background region, 1.3. It's a little more complicated than that. There's a Bayesian formula to actually work that out that's in the reference here, but that's sort of what this is getting at, is that signal to noise ratio in X-ray astronomy is not the same thing as significance of detection. We're very confident that the count rate in this region is greater than 0. It's just we're only able to measure how big the flux is to, you know, a factor of 3 or so. So unlike optical or radio astronomy, X-ray measurements are usually reported in actual CGS flux units, ergs per centimeter squared per second over some bandpass. Most of the focusing telescopes are operating at soft X-ray wavelengths, so something like 0.3 to 7 or 0.3 to 10 keV. To convert from the measured source count rate, we need information about the spectrum of the source. X-ray detectors are operating over a much larger range of energies, almost 2 orders of magnitude in energy, you know, from 0.1 keV up to 10 keV, for example. Unlike optical imaging, where you're looking over a relatively narrow range in wavelengths, the shape of the spectrum really strongly impacts what the flux of your source is. Now, sometimes when you only have a couple of counts, you actually just have to assume some spectrum. You know, you can't actually measure what the spectrum looks like if you only have 10 counts in your bandpass. But for higher count rates, you can actually model and actually fit a spectrum to the data, and then use that to convert the count rate that you measured to the flux, ergs per centimeter squared per second, over some bandpass. How do you go about doing that? You need 2 particular pieces of calibration. One is called the RMF, or the redistribution matrix file. I think most people don't even know what that stands for, so you can just call it the RMF. This is effectively just telling us the probability that a photon of a given energy will be detected in a given channel, or in a given sort of energy band, if you will. So you can see here the Chandra ACIS, the primary imaging instrument on Chandra RMF. It's pretty linear and shown as, you know, kind of a linear scaling on the left, not surprising. There is some spread, you know, it's not perfect. You don't always know, based on what channel photon is detected in, what its true energy is. That's all that the spread in this RMF is effectively telling you. And then the other piece of information that you need is called an ARF, or an ancillary response file. This is just telling you the effective area of the telescope as a function of energy. This changes, you know, pretty significantly across the X-ray bandpass. You can see for, again, Chandra ACIS down here at 0.5 keV, the effective energy is only, you know, 10 centimeters squared, whereas at 2 keV, just a factor of 4 in energy, it's, you know, a factor of 20 or so higher. So the effective area of the telescope varies quite significantly as a function of energy because of the properties of the mirrors largely. And also to some extent the properties of the detectors. So the response, the file that you really need is the product of the RMF and the ARF, and that allows you to take an observed spectrum and use that to convert a count rate into an actual flux measurement. So with that, I think I will wrap up here. I wanted to thank everyone for listening. I'm looking forward to seeing this year's participants at the time for our follow-up live discussion and hands-on Python tutorials, which I'll be leading for X-ray astronomy. This lecture and the Python notebooks from our tutorials will be made available to anyone on our website after the school. As a reminder, that website is growth.caltech.edu/astronomy-school.html. Head to this webpage, download our resources, play around, ask us questions. We're really happy for people to be engaged and to interact as part of this process. Thank you very much for watching.